Okay, so I would like to thank the organizers for giving me the opportunity to speak. And as Jan said, this talk will be about parabolic quasi-contact cone structures with a transversal infinitesimal symmetry. Just to give you a very quick idea what the story will be, so we will consider a class of parabolic geometries, so we call them parabolic quasi-contact cone structures. They include in particular conformal structures, so of pseudo-Riemannian conformal structures, and certain generic distributions on low-dimensional manifolds, namely 2, 3, 5, and 3, 6 distribution. And we will show that if we have such a parabolic geometry together with a transversal symmetry, then we obtain on a local leaf space a geometric structure that's related to ODEs that are variational. And conversely, if you have such a variational ODE type geometry, then it arises from such a symmetry reduction of a parabolic quasi-contact cone structure. So that's the main sort of story that I'm going to tell. We can also associate a canonical Cartan connection for these sort of ODE kind of geometries, which allows us to investigate sort of classes of these geometries, also to say when they are actually variational. And in the very end, I might say a few words about how we plan to further apply this geometric picture. There's a little bit of literature. So first of all, in the very end, so that's joint work with Omid, and we are writing on a paper. And maybe I should also say, so in particular, the first part of the talk is very much influenced by work of Chapp and Salaj on parabolic conformally symplectic structures and the relationship to parabolic contact structures with a transversal symmetry. Okay, so let me start with the sort of simplest or most familiar geometric structure. So let's start with the conformal geometry of some signature p plus 1, q plus 1. Now to do our construction, we will first pass to the projectivized null cone bundle. So if we denote the total space of this bundle by m tilde, so if our conformal manifold has dimension n, then this would be now, the total space would be a manifold now of dimension 2n minus 2. And it's canonically equipped with a certain filtration, namely first it comes with a tautological bundle, namely like a point in this null cone bundle is now a null line in some tangent space, and a vector would be contained in this distribution t minus 1m here if its projection down is contained in the null line that defines the upstairs point. So we have this distribution. Moreover, this distribution splits, namely it splits into the vertical bundle V and a line bundle which corresponds to the null geodesic flow. So we have this distribution with this splitting, and moreover the distribution is a non-integrable, and if we add Lie brackets of sections of the line bundle and the vertical bundle, we get, so the next part in the derived, we get a hyperplane distribution, which is here denoted by t minus 2 m tilde. And this distribution is actually a quasi-contact distribution, so it's itself maximally non-integrable, but it's now maximally non-integrable on an even-dimensional manifold. So in particular, locally it's the kernel of a 1 form, such that when I restrict d alpha to the distribution, this has maximal rank, which means in this case that it has a one-dimensional kernel, and that's the characteristic line bundle. And that's precisely the line bundle E. So that's the geometric structure we have on this null cone bundle. Now, we will not only consider conformal structures, but we will consider also a generalization of conformal structures, which corresponds to the same kind of filtered structure. And they were studied in Omit's thesis, and here sort of one replaces the null cones by more general cones with so more general hypersurfaces in the projectivized tangent bundle with non-degenerate second fundamental form. So that's the first kind of geometric structure we have. Then we look also at 235 and 36 distribution, and here we proceed in a similar way and get a similar kind of structure. So in this case, we would start with the distribution and then look at the projectivization of the distribution. So that's now the total space of this bundle is now our manifold M tilde. Again, this is equipped with a tautological distribution, which is called T minus 1M. So it's defined just in a similar way as before. Again, this distribution is bracket generating, so you get a filtered structure. The filtration is now longer, but also in this case, the last non-trivial bundle will be a quasi-contact distribution as before. And the characteristic, again, it has a characteristic line bundle, which is denoted by E, which is transversal to the vertical distribution V, which is also contained in the prolongation, so in the tautological distribution T minus M tilde, which has the same rank as the original distribution. So we have a similar kind of geometric structure here. We've referred to all of these kinds of geometries, so 1, 2, and 3, as these parabolic quasi-contact cone structures, because we can describe them as such sort of subbundles in the projectivized tangent bundle. Quasi-contact because we have these quasi-contact distributions and they are all parabolic geometries. So let me very quickly give you the description of as parabolic geometries. So they are equivalent, these quasi-contact cone structures are equivalent to regular normal parabolic geometries of type GQ, so Q parabolic will be denoted by Q here, of one of the following types. So in the causal case, we have parabolic geometries of type SOP plus 2, Q plus 2, and the parabolic being the stabilizer of a null line contained in the null 2 plane in the standard representation. So in Dynkin diagrams, that would be the parabolic, the parabolic that's depicted in the middle with the two crosses. So on the homogeneous model, we have a double vibration picture, which kind of reflects the fact that we have always this splitting of the distribution T minus 1 M tilde. And on the left-hand side, we have the model for conformal structures. So in parabolic geometry language, we pass from the conformal structure to its correspondence space. And the upstairs geometry is simply more general than the conformal geometry here. So the geometry is locally a correspondence space over something conformal if and only if one of the harmonic curvatures upstairs vanishes. So these are the parabolic geometries corresponding to the causal structures. Then we look at, in the G2 case, we look at G2 mod the Borel subalgebra. So that's again the Lie algebra on the top. And these are always locally correspondence spaces over the parabolic geometries corresponding to 235 distributions. And finally, we look at parabolic geometries of type SO34, and the parabolic being the stabilizer of a null 2 plane contained in a null 3 plane. So that's the last picture which we get. So these geometries we get if we look at correspondence spaces over 3/6 distributions. One more thing is I've drawn a double vibration. So for all of these geometries, the models also have a one-dimensional vibration over a parabolic contact geometry on the right. Maybe I have that on the next slide. So the parabolic Qs that we are looking at, they're always codimension 1 subalgebras in parabolic subalgebras corresponding to some parabolic contact structures, and that's somehow also how you can get the list. So you look at the list of our geometries. So you look at the list of contact geometries, and then, and then actually you cross, if you have a single node next to a crossed one, you cross that as well. Anyway, so that's the one remark. The other one is, these are parabolic geometries like most, but anyway, that are completely determined by the filtration. So the parabolic Q is the non-negative part in a grading, which is denoted, goes from Q minus K to QK. And the geometric structure is given by a bracket-generating distribution that has symbol algebra, precisely this Q minus. Okay, that's the parabolic geometries that we're looking at. Now we assume that we have an infinitesimal automorphism of the structure, and we assume further, we call it transversal if it's not contained in any, if it is nowhere contained in the quasi-contact distribution. So it should be transversal to the quasi-contact distribution. That's always the case, at least on an not everywhere, but at least on an open-dense subset, which is essentially all we care about. And if we have an infinitesimal symmetry of, say, a conformal structure or a distribution, then this will lift to an infinitesimal symmetry of the corresponding parabolic quasi-contact cone structure. Now, I want to describe the geometric structure we get on the local leaf space. So we can now pass, so we get a foliation, we can pass to a local leaf space. So I will give you now, in particular, this geometry will inherit the geometric structure of the following type here, but it will be a little bit more special than that, and I will come to that later. So now I define a parabolic, almost conformally quasi-symplectic structure as a geometry that's given by a bracket-generating distribution that has a weak-derived flag and a symbol algebra that's at every point isomorphic to a Lie algebra S minus, which is the quotient of this Q minus we had before by the last part in the grading. So I just cut the grading and remove the last part from Q minus. So I have such a filtration, and I also have a reduction of structure group of the graded frame bundle to a subgroup of the graded automorphism of this S minus, which corresponds to the graded automorphism of the Q minus. So to the Q0 from before. And in particular, I get such a structure if I start with a parabolic quasi-contact cone structure and go to the leaf space by transversal infinitesimal symmetry. Now, let me briefly describe what these structures are for the individual groups. So first, if I start with the groups for a causal geometry, so SOP plus 2, Q plus 2, and the corresponding parabolic, then the filtration I get will look like the filtration for a path geometry that we've seen already today. So in particular, I get a distribution. It splits into a rank 1 bundle and an integrable subbundle. And so one of the data I get is a path geometry. But the reduction of structure will give you more. So in addition, we will get a conformal, something that one can describe as by a conformal class of metrics on the vertical, on the integrable subdistribution V. And we call such a structure an orthopath geometry. So that's the first part. Now, if we look at G2 and the Borelli subalgebra, here we get a geometry that corresponds to the geometry of a fourth order ODE up to contact transformation. So geometrically, one can describe such an ODE geometry as a hypersurface in the space of 4 jets of maps from R to R, which is locally diffeomorphic to the 3 jets, projects locally diffeomorphic to the 3 jets. In particular, it has a filtration like on the jet space, and the equation is in addition encoded in an additional line bundle denoted by E. So that's the line bundle corresponding to the foliation by lifts of solutions. And now you can see that, so that's what the Dinkin diagram shows you, that you can see that the filtration you get if you do precisely what we said. So we look at G2 and the grading corresponding to the Borel subalgebra and look at the negative part and quotient out the last bit. Then the filtration we get looks like the one on for such an ODE. So we have on the one hand this line bundle, which corresponds to, which is spanned by the total derivative. Then we have the vertical bundle for the projection onto the next jet space, and then the Lie brackets just move you up. Finally, the last geometry will be a geometry that contains the geometry of pairs of third order ODEs up to point transformations. So that's the geometries we get. So now the next thing I want to do is we will associate. So we're having these geometries. Now we want to associate a canonical Cartan geometry to these types of geometries, which actually already is done for the geometries of ODEs, but we also want it for our orthopath geometry, which is kind of a further reduced geometry, but that can be done in a very similar way. And I don't want to say too much here. I just want to tell you what type of Cartan geometry one gets. So the big group. So we will get an equivalence of categories between these parabolic, almost conformally quasi-symplectic structures and regular normal Cartan geometries of type S and S upper 0, where S is a Lie group which has the following Lie algebra, namely if you consider the contact grading corresponding to the groups we've been looking at. So then one takes the opposite parabolic, so the negative part and G0, and factors out the last bit. So it's actually just something like P minus 1 plus P0 for the contact grading. That's the bigger group. And the smaller one would be this P0 intersected with the parabolic Q. Because I don't have so much time, I'm not going to say much about the normalization condition, but sort of how in a similar way to how it's done for these other ODE geometries, one can construct a codifferential to define the normalization condition. And then once we have that, it's also from this algebraic picture easy to see that these geometries always come with a distinguished line bundle of forms of maximal rank, and since we are on a manifold of odd dimension, this means again that they have a one-dimensional kernel. And in general, this line bundle doesn't have to have closed sections, but if it has closed sections, we call it parabolic conformally quasi-symplectic, so one can drop the almost. And now the point is that if we quotient for the reduction by transversal symmetry of these parabolic geometries that we have, they will always have such closed sections. And if any of these structures that are quasi-symplectic can be locally realized as the quotient of a parabolic quasi-contact cone structure. the argument maybe, I always forget how much time.
Sorry, no hurry, 10 minutes.
10 minutes, okay. So, I mean, like the reason why we always get this closed two form is that suppose we start with our parabolic quasi-contact cone structure, then, and we have a transversal symmetry, then we can take the quasi-contact form that is, say, 1 on the symmetry, and for this contact form, it's then easy to see that, first of all, the symmetry, hooking the symmetry into the alpha gives 0, and then as a consequence, the Lie derivative with respect to the symmetry of the alpha will be 0, which means that the alpha actually descends to a closed two form downstairs, which is a section of this line bundle from before. And then for the converse, I mean, I'm not giving the whole proof, but if we start with if you assume that we have a closed section, then we can take it is locally d beta for some one form beta, and now we can define as our manifold M tilde the product of U with R, and a quasi-contact form, which is just the pullback of this beta plus dt, where t is the R variable. So this will give a quasi-contact structure. We can also leave the rest of the geometric structure, and the symmetry will just be given by partial t. Yeah, so and then now the last part is, so we have these quasi-symplectic structures we can always arise from such a symmetry reduction. The last part is now this quasi-symplectic, there should be symplectic condition, so that we have this closed two form means that the corresponding ODEs are actually, structures are actually variational. I'm not going to explain, so there are different ways of seeing this. In particular, this is implied by results about, I mean, there's a lot of literature, but by Anderson Thompson, which gives a characterization of variational, at least systems of even order, in terms of the existence of a closed two form with certain algebraic properties that we have. Now, in the case of fourth order ODEs, this was actually studied in detail by Mark Fels. So in this case, first of all, if you look at the geometry of fourth order ODEs, then it's known that one has 4 fundamental invariants, which are so scalar invariants. So 2 of them are the Wilczynski invariants, and then there are 2 more. And then these ODEs are variational, so multiples of Euler-Lagrange equations for a non-degenerate second order Lagrangian if and only if the 2 of these invariants vanish. So geometrically this would correspond to a sub-Finsler structure on a contact 3 manifold. Equivalence classes of such Euler-Lagrange equations would correspond to divergence equivalence classes of the Lagrangians. And now, if we are in the situations that we are variational, we can quasi-contactify and obtain a 2-3-5 distribution plus a symmetry. And I mean, I didn't really talk about this, but we can also relate, in this case, the sum of the invariants of the downstairs geometry to harmonic curvatures of the upstairs geometry. So in particular, the last remaining Wilczynski invariant in this case would be related to the harmonic curvature of the upstairs parabolic geometry, and in particular, if this invariant vanishes, then the corresponding 2-3-5 distribution would be flat. And there's a 2-parameter family of such structures. Okay, so finally a few words about the other geometries. So for variational orthopath geometries, these would correspond to divergence equivalence classes of non-degenerate first-order Lagrangians, or equivalence classes of generalized Finsler structures, which Omid should explain, because he knows these For variational pairs of third order ODEs, because they are of odd order, the corresponding Lagrangian necessarily has to be degenerate. So here we get some strange degenerate Lagrangian, which is linear in second order derivatives. Yeah, and now a few words about sort of how we hope to apply these ideas further. So the point is that for parabolic geometries of geometry, there are families of distinguished curves. In particular, if one considers contact geometries, one has chains. And now the idea would be to use these geometric pictures to show for some of these classes of curves whether or when they are variational. So like an obvious idea is to look at chains for CR structures, because here there's a Pfefferman construction that associates to the CR structure a conformal structure on a circle bundle over the manifold, and this always has a null conformal killing field. So we have our symmetry, and one also knows that null geodesics of these conformal structures protect the chains. On the other hand, if we have chains, we have an associated path geometry of chains, which actually gives, and actually what we get is a factor through an autopath geometry. So the idea would be that this autopath geometry should correspond to the variational, should be variational, so it should correspond to the variational autopath geometry that one obtains from the null conformal killing field. And that's all.